welcoming you all once again to this channel. Today I am going to make another video on the VASP tutorial series. So earlier we have seen many different kinds of calculation that can be performed using this VASP software, and all these simulations are DFT simulation only. So today, in continuation to all those previous videos, I am going to make a video that will be based on this Ab Initio Molecular Dynamics calculation, that is the AIMD simulation. So how to do that and what kind of input tags we required for those kind of calculation, that we will see in today's video. So here I have some inputs and output files for a particular AIMD calculation. So before going ahead with the input files, I will be showing that what kind of structure we have used to perform this calculation. So here I am opening my Vesta software, and there I will be open that Postgre file. So here you can check that this is the kind of a slab, like this is this Ti3C2O2 magazine, and here you can see that we have this slab, and above to that and below to that we have certain vacuum, and this vacuum is entirely added up to 15 angstrom, and this is just a simple slab and where we will perform this molecular dynamics calculation. Okay, so next is I am going to open the incar file where we will see what kind of tags we are using for this calculation. So as you can see, this first part is nothing but the standard DFT simulation, like the standard optimization values that we have already discussed previously. And here I have not taken this spin polarized calculation because this TI based magazine, like these are this is a kind of non-magnetic material where the upspin and downspin for this titanium is cancelling each other. That's why if you want to take, no issue, like it will be very less, the magnetic moment you will get very less, so you can simply ignore. So to reduce this cost, I have like commented out these tags. And next, this is also very like standard values, like where we are given this force convergence and energy convergence and the cutoff, like that. And next, this portion is is the main part. So here we have added 5-6 tags for this AIMD simulation, where the first tag is IBRION0. So by the side by side we will also see these tags from the VASP wiki. So here I have this VASP Wikipedia, so I am going to open it, and here I will be searching this. Let me search first AIMD. Yeah, no such tags are available. It might be available on the home tag. Let's see. Here is one molecular dynamics. No, not exactly, but it's okay, you can also check from here. Otherwise simply we can go we can search IBRION. Okay, so you can also see here that IBRION can have this much values, and each value like -1, 0, 1, 2, 3, every each value is assigning some different things in this while performing DFT. So you see this IBRION is equal to 0 is mainly for the molecular dynamics. That's why we have said here IBRION equal to 0. So typically we use this IBRION2 for conjugate gradient and IBRION3 for damped molecular dynamics. This kind of we use while doing this structural optimization, and sometimes IBRION1 also when we have very exact input files. So this kind of thing we use, but for molecular dynamics we should use this IBRION equal to 0. Next is MD algo, so that also I will be showing you here. So yes, here you see MD algo is related to this IBRION. So here I am clicking on this MD algo. You check over here that MD algo specifies the molecular dynamics simulation protocol. In case IBRION equal to 0 and VASP was compiled with DT dt by dyne. Okay, so when we are doing this molecular dynamics calculation using IBRION 0, so that time we need to provide this MD algo. So we can go also down here. You see that MD algo can also have like various such numbers, and 0 is for standard molecular dynamics, 1 is for Anderson thermostat. We know that various thermostat like thermostat, barostat is available here. So this 1 is for Anderson, and next this MD algo 2 is for nose over thermostat. Then this way you can see various thermostats that are here. Is MD algo 3 is for Langevin thermostat. So this way one can took whatever he or she wants. So this way you can see various numbers are assigned to various thermostats. And here we have taken this MD algo is equal to 2, that is this nose over thermostat. You see here for the description of the nose over thermostat, see nose, here is the option. You can also click on here that what is that means and how it is compiling the Lagrangian for the system using this particular thermostat. One can be read from this, and some related articles like here some references are given. You can also use that, like you can refer that. And okay, so here this nose over thermostat, what it will do, like it will maintain our system within a specified range of temperature. And for that we need to also provide some other input parameters. So here you can see the standard molecular dynamics involves set the standard MD related tags like IBRION 0, TBG is nothing but the temperature beginning, and port IM, NSW. So all these things we need to do here. And here this is the for constant molecular dynamics you can also use different, like here this iconst file you need to provide. So various things are like given over here, but typically we use this much things and for a standard molecular dynamics. So as you can see here I have used this TBG and T end. That means this temperature beginning and temperature end is 300. That means we want our structure to be maintained at the temperature 300 Kelvin. Okay. So this part is done. You can see here I can also click to show that what is TBG. TBG is sets the starting temperature in Kelvin for an Ab Initio Molecular Dynamics run. Here you see every time it is showing that IBRION equal to 0 is must for the AIMD simulation. And similar way T end is also another tag. You see here TEND, it sets the final temperature for Ab Initio Molecular Dynamics run. So this way we can do. And next tag is the SMASS. So let's go to SMASS. So SMASS controls the velocity during the Ab Initio Molecular Dynamics run. So actually to get a particular velocity for a system, you need to first test with various SMASS values for a particular system. So I have tested with 1, 2 like that, whatever it has given over here. Then at the end I found that with this SMASS 5 my system is running quite well. That's why I have set it out. But here some descriptions are also available. We can refer that. Here you see SMASS equal to -3 is a microcanonical ensemble, that is this NVE ensemble is simulated at constant energy. So it depends like what kind of ensemble you want to use for your system. That way you need to check. Okay, so mainly this -3 value is for in microcanonical, that is this NVE. This -2 is also for different, like the initial velocities are kept constant. So it depends what kind of calculation you want to do for your system. And next here the important tag is SMASS greater than or equal to 0 is for canonical ensemble. So here I have taken this value of 5 which is coming in this range. That means we are interested to do this canonical ensemble simulation, that's why. And also using the nose, so here we need to use this nose. That's why we have already taken this MD algo equal to 2, which is nothing but this nose over thermostat. So okay, so this way you can perform like some like test simulation, then you can fix all your parameters, then you can go for your final run. Okay, next part and very important part is this port IM. So what is this port IM? So let's go to that. So here I am clicking on this port IM. So you see that port IM is none and must be set if IBRION equal to 0 for MD. So it should be, you need to set this value. Why? Because port IM sets the time step in molecular dynamics or the step width in ionic relaxation. So port IM should be given in a molecular dynamics simulation, because it will provide the time steps. You see here it gives the time step in femtosecond. In all Ab Initio Molecular Dynamics run, it has to be supplied, therefore otherwise it has to be supplied, otherwise VASP crashes immediately after having started. Okay, you understood. So what we need to provide is the port IM value, which will decide the time step in connection to this NSW value. So here you see that I have given the port IM value as 1. That means I have given it as 1 femtosecond. 1 femtosecond is 10 to the power minus 15 second. And here I have taken this NSW value as 10,000. Okay, so this way you can see that how long your simulation will go ahead. Okay, that means if I have given this simulation as 10 to the power minus 15 plus 10 to the power 4, so here it is having 10,000. This entire simulation will become a 10 picosecond simulation, like 1 femtosecond in time step and this 10,000 steps. So this way one can simulate this AIMD simulation, and this value is just for the van der Waals correction terms. Okay, so next part is we will see now the contour. So how the contour of this file looks like. So here you see, like this is actually during the simulation. So when you will provide some temperature, then the system will try to rearrange themselves, like they will be deformed sometimes, and again during after the optimization they will come back to the original position. So this is just during the like optimization I have taken this contour file. So you see this is what happens after AIMD simulation. Okay, so this way you can perform, and also I can show you the output file. So here the VASP.out file I have. So you can see here it is like one first simulation, you see this temperature in 194. So this way it will vary from that range, 194 sometimes 190. So this way it is going on, and you will also see 164, and again it will come it will increase and decrease during the steps. And this is how you can simply perform. You see here 218, 218, 217. So this way it will vary from that like near to that range. And you see here 357, 355, and near to that range it will lie always. Okay, so this way one can perform this AIMD simulation. And thank you all. This much for today's session.